And this we're going to see tooth elastic static analysis. Let's import the part of the tooth it's based on the actual research paper that we could see here. So let's have this. This is a tool that we have imported. So for the property I have actually has a library of tooth. Let's over here buy tooth and then so this one. So you can see the density that as per the journal that they have given. So these are the values that he have given on the journal. So we are considering that same material that we want. Okay, so let's consider it and everything done. So we are done with the thing, and then now since it is a simple one, so import it. So and then let's start with the step. So go over here. It's a simple static general, and then let's on it. No need of this, and then increment. So reduce this and then increase some number on this and let's go for increasing, reducing that. Done. So we have created it over such a way and then let's go to interactions. So it's pretty much like easier one that you can see. Let's create a reference point over here. So I'm just taking a reference point such a way that it will be easy for us. So I'm just going to create a two sets. So let's create burst set. First set as um, load area that we are going to queue uh, area that for these two sections. So let's create a set for that. And then let's take tools and create a set for boundary conditions. Let's take for boundary conditions. Okay. So if we take the boundary conditions, let's select all. Now what you need to do is unselect things. So you get this bottom portion that which is going to be fixed as boundary condition. So done. Now initially I want to create a coupling so that that will be easy to give the load. Oh, this will be our done, and then surface we can have the uh, this and this. Okay, done, done. Yeah. So we have these surfaces. Okay. So since we have these things, go to step create a new history output required for the set as per such requires boundary condition. So since it is a boundary condition, we are in the reaction force of R2. Okay, right? Okay, done. And then create step. Yep. So for the set which is required for load, so load area, the area that the requires load, that's we going to be cycle displacement of U2. Okay, so that's good to go. Let's go to load. So let's create a load of concentrated force, which for this RP done. Then we are going to give load of minus 0.4 kg Newton. So that's why it's pretty low. Like, okay, then let's create a initial of schematic and then let's create a set of boundary condition that we have created earlier. So, okay, now the boundary conditions and the things are ready. So, next is our top priority of meshing. So let's get into here and then let's assign first. Okay, so now we're going for is tetra. Okay, now tetra, let's give a global mesh size of 45, click OK, and then mesh it yes to go. So we have a tetrahedron. So just pretty good that you can see that it's a solid tetrahedron. So let's assign what kind of thing, which is a static. Let's go for linear. That's its better. So 3D stress. Okay, right. So let's check with the job and then let's run it. Create job. Let's take to static. Go for the parallelization. Let's go for it and then select monitor. Let's look into it. As you can see, this analysis has been completed. Let's look into the results that we are going to see. So you can see the stresses that has been distributed such a way at the midsection of the tube. So it's pretty high, the points that you can see it's pretty high, even though you can actually have the option of limits, so you can specify specific options that either you can use 25,000 apply and see how it is pertaining, like see, okay, over here. So it start to have the compressions and you can see where the stresses are more higher, which is actually basically midsection. Even you can go even lower like 20 and then give a play. You can see where the higher stresses are, like even more spread at the midsection, right? So you can either function it and then it's pretty fast, and then slow it out. You can see how it spreads outwards as the it spreads. You can see it out, and it's pretty much cool to see it out that way. With respect to displacement that you can see now, since the limits actually been there, auto limit apply. Okay, so now you can see it. It's been like this, and then you can see it's a single direction oriented thing. Let's go for U2. That will be like pretty much clear about things. So you can see there is a negative range. So that's why the contours are different in way. So that's it.